Swayam Prabha. Digital India. Educated India.
Welcome back, guys. So we're talking about compounds that are organic, covalent bonding, organic compounds. And we're going to talk about isomers, which are just part of, the whole family of organic compounds, isomers. What are isomers? Isomers are things that have the same molecular formula but different structures. So compounds with different structures but have the same molecular formula. Let me write that down because it's important. A molecular formula tells you how many different elements are there and how many of those elements are in a formula. For example, C6H6. That means you have carbon and hydrogen, 6 carbon and 6 hydrogens in one covalent bonded unit, which is what we call a molecule, right? So isomers, how many types are there? It turns out there are quite a few, and we're going to talk about constitutional isomers, but I'm going to just write all of them down, and then we will talk about the others as we go along. So today we're only going to talk about constitutional isomers. Constitutional isomers, so your constitution, what you made up, your backbone can be rearranged here, constitutional isomers. So that means you have the same molecular formula, same number of the same elements. However, you're connected differently. Okay, different connectivity, same molecular formula. That again, because the molecular formula cannot change in any of the isomers. Same molecular formula, but different connectivity. And we'll look at that in a minute. What's the other type? The other type are stereoisomers. Now, how are they different from constitutional isomers? Here, the same molecular formula and same connectivity. Same molecular formula, same connectivity. Over here, for example, if I take a molecule like this, here's carbon, 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 carbon. Let's just take 4. If you have only 2 carbons or 1 carbon, you can't have any isomers. For example, CH3, CH3, let's say. There's only one way you can fix this. There's no other way that you can fix 2 carbons, right? And same with 3 carbons. They have to be in a row. So if you have 1 or 2 or 3 carbons, there's no constitutional isomers possible for that. All right? And if you, let's say, you put another carbon, carbon number 4. So here's, well, I'm drawing them zigzag because as we talked about earlier, these carbons are tetrahedral structures, 109.5 between these. Therefore, you won't get them straight line. They're not 180 because of sp3 hybridization, right? So therefore, all of the carbons that you're going to draw will be zigzag. So here, so when you get to 4 carbons, is there something different that you can do? Right? You can branch them. That's right. You can take the N carbon, put it in the middle. So same molecular formula. I didn't change the carbons or the hydrogens. Let's assume these blue little sticks are hydrogens. I didn't change the number. I just changed the way they were connected. So that's exactly what we mean by constitutional isomers. When we come to stereoisomers, it's a little different. For example, if you have a double bond like an sp2, you can have, this is the same connectivity, carbon to carbon to carbon. It's the same connectivity, no difference in connectivity. So what we mean here by stereoisomer, this is one type of stereoisomer, the geometric isomers. So here, let's say this is your pi bond or double bond. All of the carbons like connected in a row like this, and this is just a double bond in the middle. So here, you cannot rotate these. like a single bond, you can rotate, you see. So these are conformation changes, whereas in a double bond, you really cannot rotate them. So you're keeping them like this, and here you have a double bond. Now I can take this, break this bond, and connect it below, but on the same carbon. So your connectivity is not changing, carbon to carbon to carbon to carbon. That connectivity is there. You're just changing the way in which it is attached, in what spatial orientation it is attached. So stereoisomers are all about different spatial orientations for the same molecule with the same connectivity. So you're not changing the way carbon or hydrogens or oxygens are connected in a molecule. They're connected to the exact same things, but they are different spatial orientations. That's what you call stereoisomers. Here's another type of stereoisomer. This is just changing the angles, the dihedral angles between this and this at the back. They're changing. That's all is happening. We're not breaking any bonds and fixing them like we did with the constitutional isomers. So this is also a type of stereoisomer. Okay, that is going to be two types, and we are going to, let's say, have conformational This is by rotation, like I just showed you. And you cannot separate them because, I mean, this molecule is just going like this, like 10 to the 9 times per second. It's going to be rotating. How will you isolate this from this? It's impossible. So these cannot be isolated, cannot be separated. These can, you can, they have different boiling points, melting points, you can separate them. Rotational isomers, that's this. Or you can have inversion isomers. So for example, let's say you have an ammonia, you have a molecule that's like this, all the bonds are coming down, and then they can flip over and go to the other form. They can go to the other inverted isomer. There you go. So you can have inversion, just like on a very windy day, when you take your umbrella out, and then when everybody's watching, it flips. And so that's an inversion isomer, both of those. Again, cannot be separated. Now, if you take the other type that I showed you, where you have a double bond, and you can have it either on opposite sides, or you can rotate it. You have to break the bond and fix it on the other side. Same connectivity, but spatial orientation is different. So those are configurational isomers, conformational and configurational. We're just learning a lot of lingo, organic lingo here. Configurational. And the one we just talked about, we can call them geometric isomers. That means you can have, or you can have it on the same side. Those are geometric isomers. Or you can have what you call chiral isomers, and we're kind of getting ahead of ourselves. I'm just going to write that down, stereoisomers. They can be with chiral centers, or you can, just means you don't have a plane of symmetry. Okay, that's what it means, no plane of symmetry. And we will dedicate an entire chapter to learning about this. And here you can have two types, diastereomers or meso, that are not mirror images, or you can have mirror images, and we'll call them enantiomers. I'm just writing them down, guys. Don't worry about them. We'll talk about them later. All we're going to talk about today, I just want to show you the classification. So rotational isomers are called conformers or conformational isomers. They're just different by an angle. Or inversion isomers. That's the umbrella. That's like ammonia, let's say, going from one side to the other. Don't worry about that. We'll come back to that. Let's talk about constitutional isomers. So as we said earlier, you need to have, well, if you have CH4, 1 carbon, or 2 carbons, or even 3 carbons, no isomers are possible, because there is no way, even if I break this carbon and bring it over here, it's the same molecule. So these have no isomers. Let's look at 4 carbons then, CH3, CH2, CH2, CH3. We had a long chain, and then we took the long chain, so that's this, and we can draw them zigzag just like this. Because the hydrogens don't have to be drawn in. Each of this, the vertex here, these are carbons, the points. Now we can take this, and if you put it here, it's the same thing. If you put it here, then it's a branched molecule. It is different. You would agree. So basically what I'm doing is taking this carbon and moving it to the middle. Instead of connecting it to the end, you move it to the middle. And so I'm drawing these line diagrams just so you would get used to them. So you can say that if you have more carbons, there's more ways in which you can break and refix them, right? So the number of isomers is going to increase as you increase the number of carbons. Let's put another carbon here and see what happens. C5, and we know the formula for the saturated. We are only doing alkanes for right now. Cn, H2n plus 2. So 2 times 5 plus 2 is 12, and that will be pentane. So these are the butanes, butane or N-butane, and this is isobutane because it's an isomer. It's like the most basic one. So C5H5, we can draw this out. CH3, CH2, 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 CH3, right? So let's draw that out. CH3, CH2. That's 5 carbons. The middle carbons will have twice the number of hydrogens because you can only have 4 for the carbons. The caps will have the 2 and the 2 N caps. So that's why it's Cn, H2n plus 2 alkanes. Now, we'll draw this as a dot structure. 5. So what are the possibilities? Say I can draw this out like this. Is this an isomer? 1, 2, 3, 4, 5. Same connectivity, same formula. Same formula. So no, that's not an isomer. So just because you bend these around doesn't mean they're going to be isomers. They're all the same. So bend, that's just rotational. That's just rotations. We are interested in breaking a bond and fixing it somewhere else. So what are the possibilities for this molecule? You can take this and just like we did earlier, move it to the middle. That's one. So break that bond over there, move the hydrogen over here, and move the carbon here. So that's one branch out there. So you can do CH3, CH2, CH, CH3, and here's a line. So that is going to be, if I were to draw it like this, so this is the same as this. If you were to draw it out with a condensed structure, or so condensed with lines between carbon-carbon, CH, CH3, CH3. So you know each carbon is connected to 4 things, so we're not violating any octet rule there. What else can we do? How about taking this N carbon, instead of putting it here, how about I put it here? Is that going to give me a different molecule? What about this? Well, kind of like what we had before, except that it's switched, right? So it's the same molecule as before. So this molecule is the same as this. All I did was take this and rotate it. So this is the same molecule, whether I have it here or here. It doesn't really matter. So this is the same as if you took this and put it here. So this is the same as this. Just to make it look the same, I'll just draw this up. So this is the same as this. Is there anything else that we can do? Anything else that we can break? If I break this and bring it here, it would be the same thing. Anybody? Well, you can really move this to the middle. So if you move this to the middle here, now this is completely different, right? So this is going to be a molecule where you have a carbon. This carbon actually moved to the middle. It's the same as moving this carbon to the middle. So that's going to be 1, 2, 3, 4. So there are 3 distinct isomers here. One is a straight chain. There's only one way in which you can fix that. Another one is where you have one branch in the middle. So this is your second one, which is the same as this. They're all the same. And the third is when you have it branched like this. So you have 3 possibilities. You can't really branch any further. This is like maxed out on the branching. Let's do one more and see how many more we can do. If you're wondering where the hydrogens are, each of these is a carbon, CH3, 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 and there's no hydrogens in the center. So there's 12 hydrogens for each one of these. So we cannot change the number of carbons and hydrogens. That's the definition. Molecular formula is the same, but we connect it different. So let's go to the next one. So we went to C4H10, C5H12. Let's do C6H, 2N plus 2. N is 6, so that is 2 times 6, 12 plus 2 is 14. What is the most obvious way in which we can fix this? As before, what's the best way to fix this? What do you think? Don't start somewhere with some branch structure and then try to draw it out of there. Start with a linear structure. Here we have 6 carbons here, and all of these, you can draw them like this, draw them like this, draw them like this. They're the same thing. They're just rotational isomers. And here we're talking about constitutional isomers. It's not just a blip, blip, blip. It's actually breaking the bond and fixing it somewhere else. So here, because molecules like to have their bonds far apart as possible, the zigzag would be the best, the least energetically favored conformer. So now we're going to take this and make isomers by breaking bonds. So let's do it systematically. Break an N bond, and we can make a bond here, or here, or here. Those are the 3 possible. If you break it, put it here, it's the same as putting it here. So that's the same molecule. But look at this. Do we get different molecules by putting it here, or are they the same? They're pretty much the same, isn't it? So therefore, you can take this, put it here, or here. There's nothing like this one. Okay? So those are the 2 possibilities for breaking up the linear chain. Then we will take these and branch them out. So it's better to go in a very systematic way. So I'm going to draw these line diagrams. So because that's kind of a little easier for you, less time consuming. So we take this and move it inside. And it's going to be here. Or we can take this and move it here. Now you might think, why don't we take this and move it here? But as I said before, that is going to be the same as this. This is the same as this. It's just rotated. Just like taking this and rotating it. We're not doing rotamers. We're doing constitutional isomers. You have to break the very backbone and reform it. So now we can take this and move it to the middle. So if I say A, this is from A. If I say B, that would be from B. So let's take A and try to branch out A in different ways. So 1, 2, 3, 4, 5, 6. So here too we can take, this is A, we can take A, take this, and if you move this over here, you're going to get the same thing. And if you move this here, you're going to get the same thing. So therefore, we cannot move this. Let's try moving this. If you move this, take the N carbon and fix it. This is different. We haven't seen this branching before. So this is a different branching. Or you can take this and move it inside. That's a different branching. We haven't seen this tertiary carbon before. If you take this and move it here, that is going to be the same as this. So we've seen that before. So therefore, there are two ways in which you can move this. So just take this A, cut it up, move it here. So if you can either move it here, C, or you can move it over here, D. So you can take A, this is a molecule. It is a molecule that you can actually then cut up and move over inside. So here you're going to do C here, which is just taking the N carbon and putting it here. Or you can do D, where you're taking that N carbon and putting it over here, right here. Those are the possibilities. So we have 1, 2, 3, 4, and 5. So here is a group where you have this and you have a rotation all possible, but they're not different molecules. Can we branch this any further? Let's say if I take this, I can't really fix it here at all. That'll be 10 for that carbon. So nope, you can't do that. If I take this and move it here, we already found that structure. If I move it here, we already found that structure. You see? So we found them all. So there's only 5 possible. When you know you can't branch any further, that's the end. This is your first structure, 2, 3, 4, and 5. 5 possibilities. We can keep going here, but let's try doing something different. Let's put an oxygen. Okay. Let's put an oxygen. Okay, see if you're going to get more structures or fewer structures when you have a heteroatom. And let's try to make some double bonds. So let's say I have C3H6O. So over here, the first thing you should do is find the index of hydrogen deficiency, and we have a formula for that. So if you have Cn, it's going to be H, so N is going to be 3 here. So H2N plus 2 would be the saturated, like you can't put any more hydrogens, it's saturated, minus whatever you have here, which is M is equal to 6, and divide by 2. If you have an oxygen, oxygen can have 2 hydrogens, so it's almost like a middle CH2, which is saturated. So we don't do anything to oxygen. If you have a nitrogen, you take off 1, because nitrogen is pentavalent. And if you have a halogen, it behaves just like a hydrogen, so you add a hydrogen to the M. Nitrogen minus 1, halogen plus 1, oxygen 0. Add 0. So here you have 3 times 2 plus 2, that's going to be 8. 6 plus 2 minus 6 is what you have. And you don't add anything for oxygen. Over 2, that is 1. What does that mean? That means your unsaturation is 1. So if you take carbon and take off 2 hydrogens, you can make a double bond. You take these off, take those electrons, imagine them making a bond. So you can have one double bond. That's what it means. You can have one double bond. Or let's say you have a long chain, and you can take the chain and take the hydrogens and over these hydrogens off and bring them together and make a ring. So there's 3 carbons. So therefore, when you have one unsaturation, you can either do a ring or a double bond. Those are the 2 possibilities for one unsaturation. So this or this. If you have 2, you can have either 2 double bonds, 2 rings, or a ring and a double bond, but you cannot exceed that. So that is now going to give you a lot more possibilities, a lot more potential for this molecule because it has an unsaturation. Okay, when you're lacking something, then you improvise and do a lot. So same here. So here's 3 carbons and an oxygen. So let's draw them all in a straight line first. Then we can try to put in our double bonds and hydrogens. So one double bond, you can put the double bond here, or here, or here. Let's try it out. So this is one possibility. And do the hydrogens match up? Let's check it out. So make 4 for carbon, right? You know that. 4 for carbon, 3 for nitrogen, 2 for oxygen. That's the bond. Number of bond, 1, 2, 3, so you have a hydrogen here. 1, 2, so you have 2 hydrogens here. 1, and so you have 1 hydrogen. So 1, 2, 3, 4, 5, 6. It's perfect. Then we move the double bond inside. C, 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 O, and move it here, let's say. Then you can put your hydrogens. So here we have 1 here, so you can make 3 bonds with hydrogens. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Great. Do the same thing again. 1, 2, 3, oxygen. Move the double bond here. These are all same molecular formula. I'm just breaking that bond and putting it different places, which means you have different connectivity. And obviously, you're going to have different functional groups when you have heteroatoms. So be prepared for that. So here you have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Nothing can go on. The oxygen already has 2 bonds. 3, 4, 5, 6. Perfect. Anything else possible, or have you reached the end of our line? Should we go further? Well, look what we did here. We have 4 atoms and we can branch them. So let's try doing that. So let's take this N carbon and move it in the middle. So carbon, 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 oxygen. Do the same thing. Take the double bond, put it here. Does it matter whether I put it here or here? So is it the same whether I put this here or here? What do you think? Let me draw it out and you can look at it and tell me whether it's going to be the same or not. What do you think? Well, it's almost like taking this and bringing it over here, right? It's exact same connectivity. Double bond at the end connected to an oxygen and a carbon. Double bond at the end connected to oxygen and carbon. So the connectivity is the same. We're just looking at it from a different angle. That's all it is. So this is the same as this. What's the other possibility? Well, as before, you can move the double bond to the oxygen. Oxygen can have 2 bonds. Then you can go in and put it a hydrogen 2, and so 2 hydrogens. 1, so you have 3 hydrogens. Oxygen can have 1 more bond, so 6. Same here. This is the same molecule. The middle carbon is already 4 bonds, so don't touch that. Oxygen cannot have any more. It's got maxed out. H3. 1. So there you go. So alcohols, ketones, aldehydes, so a lot of different functional groups are possible for this molecule. Always be mindful that you're not changing the number of atoms and type. Molecular formula cannot change. That's kind of the cornerstone of this entire exercise. Keeping that the same, but changing the way the bonds are arranged. All right. What about other possibilities? Anything else, or have we just reached the end? What do you think? Yeah? That's right, we didn't talk about rings. If you can have a double bond, you can definitely have a ring, always. So let's look at rings. So you can take a ring, like if you have a 3 carbon, you can bring it together and make a ring. Or you can make a 4-membered ring. So rings are possible. So here you can have 3 carbons, and let's say you have an oxygen, you can have a ring. Only one ring, you can't have more than one ring, just because that's the formula. So here's a ring that's possible if you have 3 carbons and an oxygen. 1, 2, 3. Okay. Oxygen has, these are lone pairs, has got 2 bonds, but each of these carbons can have 2, 2, 2 hydrogens. So C3H6O. Here's a ring that's possible. So you see the formula is going to be perfect for this ring. This ring doesn't want to form because it doesn't like 90 degrees. But if I make it a little flip like that, then it's a little easier. So there you go. So that's going to be your 4-membered ring. So let's do rings. So these are alkenes and carbonyls. Let's do rings. For rings, carbon, 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 and oxygen. And each of this already has 2, so you can have 2 hydrogens here. And whether I put this oxygen here or here or here, anyway, it's going to be the same. There's only one possibility, right? So here is going to be 1, 2, 3, 4, 5. This is structure number 6. Anything else? Or is this the end of the road for this molecule? What do you think? Yeah? Think about it, guys. Turn off the computer and pause it and think about it. Well, why not contract it and make it 3 in a ring? So you can take 3 carbons in a ring. For 4-membered rings, that's it. You can't have anything else, but you can have carbon, carbon, oxygen. And then you can have a carbon outside. So let's put your hydrogens in. I'm just going to, use the same colors. 1, 2, and then 1, 2, 3, 4. 1, 2, 3, 4. It's just a matter of counting. 2, 3, 6. Good. This is our structure number 7. Anything else? Would it matter if I take the methyl and put it to this carbon? It's the same. It's just like flipping it. Flips are not isomers. Isomers when you break bonds. Can I take this carbon and put it on the oxygen? What about this? You know there's something wrong with this, right? Because oxygen should only have 2 bonds. So in this constitutional isomer, something that you absolutely must bear in mind, must, is these are neutral structures. Neutral organic molecules can have a maximum of 4 bonds to carbon, 3 bonds to nitrogen. Can have, or must have, I should say, must. You cannot have less than that if you want it to be neutral. 2 bonds to oxygen, 1 bond to hydrogen. This is something you really cannot violate. So just always bear that in mind. So here this is wrong because you put 3 bonds to oxygen. So well, let's keep going. What else is possible? How about carbon, 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 like hydrocarbon chain? And then where would you put the oxygen? Would it matter whether you put it here, here, or here? Well, let's try it out. Let's say we put it here. 1 hydrogen. So this is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So yes, you can have that many over here. Anything else that we are missing out? How about oxygen with a hydrogen is fine. We didn't put oxygen with a carbon. Well, over here we cannot do that. But let's say we can have carbon, carbon, and then we can have an oxygen carbon. Well, you can have two bonds to oxygen, right? So we can have it between two carbons. So over here, well, we need to either have a ring or a double bond. So let's make a ring here. A double bond there. So you have 1, 2, 3, 4, 1, 2, 3, 4. These are ethers. So how many do we have here? 5, 6, 7, 8, 9. Any other possibilities for this molecule? How about moving this oxygen over here? It will be the exact same thing, right? So you know that you need to have all of these structures when you have just one unsaturation. If your unsaturation increases, then you're going to have more and more possibilities. I'm just going to draw line structures for this because it's good practice for you to kind of learn how to draw line structures. So we have here 9 of this. I don't know if I can squeeze it in here. Let me draw these. 1 is going to be double bond, single bond, OH. 2 is going to be single bond, double bond, OH. We're not going to worry about geometric isomers, putting the oxygen up or down here. We're just doing constitutional isomers. So 3 is going to be 1, 2, and this. And when you have a carbonyl, you need to put that hydrogen. 3, 4 is going to be a double bond with an OH. 5 is going to be 2 single bonds with a double bond like that. 6 is going to be a box. 7 is going to be a triangle with an oxygen. 8 is going to be a triangle with an oxygen outside. And 9 is going to be an oxygen that has 2 bonds. This is just stripping off the carbon hydrogens and just drawing lines for carbon-carbon bonds. So these are line diagrams. These are expanded structures. This one especially, you can call this kind of a condensed structure. So we're here doing, kind of practicing what we did earlier. Line diagrams, condensed diagrams, and expanded diagrams. Just a summary right now on isomers. Isomers are compounds that have the same molecular formula but different structures. We're talking about constitutional isomers today. We're going to change just the connectivity of the bonds. That's all we're going to do. We're not taking off hydrogens or carbons or oxygens or any other atoms. We're just changing the way they're connected. And the bigger the molecule, the more the possibilities. So over here, here's the most simplest. Take a 4-carbon chain and we can make it into an isobutane. So that you get the idea. It's just a matter of switching bonds around. Another very important thing to remember is if your molecule is neutral, you don't have any formal charges there to worry about. You don't have oxygens or nitrogens or carbons with minus or plus. Just draw neutral structures for them, which means for every carbon you must have 4 bonds. They can be double, single, triple to any of these, but they must be 4 sticks on the carbon, 3 sticks on the nitrogen, 2 sticks on the oxygen, and 1 on the hydrogen. So the number of bonds cannot deviate from this when you're drawing constitutional isomers for neutral compounds. Another very important thing to remember is the index of hydrogen deficiency. That will tell you the number of double bonds and rings. If you have a compound where the number of hydrogens is twice the number of carbons plus 2, that means you don't have any rings or double bonds. It's saturated with hydrogens. You have the maximum number of hydrogens possible. If you put this in a huge vat of hydrogens, it's not going to touch any of the hydrogens because it's already filled, to the max, to the brim with hydrogen. So that's a saturated compound. If you take hydrogens off of this, then it's unsaturated. When you're unsaturated, you have a lot of possibilities going for you. For example, in this compound, C3, so Cn, N is 3. So 2n plus 2 is going to be 2 times 3 plus 2 is 8. And then if you subtract the amount of hydrogens that you currently have and divide by 2, that would tell you how many double bonds or rings you would have. For oxygen, you don't add or subtract any hydrogens from the formula from the M. For nitrogen, you take off 1. For halogens, you add 1. That's what you have to remember. Now, over here, when you have one unsaturation, what are the possibilities? So, if you have one IHD, you can either have a double bond or you can have a ring. Double bond or ring. So, that gives you a very, very, very large variety of different types or shapes of molecule with different connectivity. So start with the IHD. If it's one double bond, we'll start with the linear and put all the double bonds. Then rings, explore all the possibilities. Start with the biggest ring, then contract and make all the rings. Make sure that you take the heteroatom and explore all of the functional group possibilities for that. Make sure you don't put 3 bonds to the oxygen or 1 bond to the oxygen or 5 bonds to the carbon, 3 bonds to the carbon. Those are not possibilities. I'm talking with the hydrogens and the other carbon or oxygen atoms. So make sure that you, first, if you're not sure, draw expanded structures. Then as you gain more practice, then you can skip the hydrogens and draw line structures. It's really nice when you can draw line structures straight away. And that's your goal. Talk to you soon, guys, and I will see you soon. Make sure that you practice some constitutional isomers. We're trying to change the constitution here. Isn't that really important? Okay, so let's put some effort into it. All right, see you guys soon.